Further consequences of the factor theorem. A polynomial of degree n has a maximum of n zeros. An example would be the linear polynomial y equals ax plus b. So this is a polynomial of degree 1, where a does not equal 0. Solving for ax plus b equals 0 will yield 1 0 at x equals negative b on a. It wouldn't make sense for a linear polynomial to have 2 zeros or 3 zeros. If you were to graph a linear polynomial, you see that it'll cross the x-axis once. If you took, for example, the quadratic polynomial, the y equals ax squared plus bx plus c, you graph that, it's a parabola. A parabola will cross the x-axis no more than twice. And it's interesting that the maximum number of zeros possible is equal to the degree of that polynomial. Now, it's not the purpose of this video to prove this point, but it is a point well worth noting. The zero polynomial, this is zx or z of x equals 0, has no degree and infinite zeros. So this is really the only polynomial that sort of breaks all the rules, in that we don't even know what the degree of z of x is, but what we do know is that it has infinite zeros. And if you were to graph the zero polynomial, that's the x-axis. And all the zeros are on the x-axis, so the entire x-axis is the solution to z of x equals 0. Now the next point is to do with identical polynomials, or showing that, or proving that two polynomials are identical. If we let p of x and q of x be polynomials of degree n, then p of x is identical to q of x. So that means that p of x equals q of x for every value of x, all real x. If and only if p of x equals q of x for at least n plus 1 distinct values of x. So in other words, let's just say p of x and q of x are polynomials of degree 3. If we can show that p of x equals q of x for four different values of x, then we can state with confidence that p of x is identical to q of x for every value of x. So for example, let p of x equal ax plus b and q of x equal cx plus d. So two linear polynomials. We don't know what a, b, c and d are. So a can't equal 0 and c can't equal 0. So these are degree 1 polynomials. Now if p of x1 equals q of x1, so x1 is one value of x, and p of x2 equals q of x2 for another value of x, where x1 is not equal to x2, so they are distinct values of x, then we can say that p of x, or the polynomial p of x, is identical to the polynomial q of x. So we can substitute any value of x that we like, and the value of p of x and q of x at that value of x will be the same, or will be equal. Now the last point that's related to this is that identical polynomials have equal corresponding coefficients. So if we're able to somehow show that two polynomials are identical, let's say from the previous example, so this is the p of x equals ax plus b and q of x equals cx plus d, we've shown that these two polynomials are identical because they have the same value for two distinct values of x, then a equals c and b equals d. So the coefficient of x for p of x is equal to the coefficient of x for q of x, and the constant term b for the polynomial p of x is equal to the constant term d for the polynomial q of x.